Welcome to homework.
This is the answer to Chapter 14, problem number 79 from the Smith Organic Chemistry textbook. And this problem asks us about 2-cyclohexanone. And so in the first part of this problem, we are asked to sketch the splitting pattern observed for each proton on the sp2 hybridized carbons. And we're given some coupling constants, some J values, and so we can predict what the splitting pattern is going to look like here. And so it's going to be a doublet of triplets. So it's going to look like this. So triplet, and then another triplet. And it's going to look like this, okay? And so the coupling constant here is going to be the 11 hertz. So 11 hertz. And then in here, these coupling constants are going to be 4 hertz each. And so that's the splitting pattern. That's what it's asking for. So it's going to be a doublet of triplets. And then in the second part of this problem, part B, we're asked, we're told, despite the fact that HA is located adjacent to an electron withdrawing carbonyl, its absorption occurs upfield from the signal due to HB. And so we're asked to offer an explanation for this. Okay, and so the answer here is going to involve resonance structures. So here is our 2-cyclohexanone. And so we can draw a resonance structure that is going to look like this. So we can break one of those double bonds. Okay, and so at that point, we're going to have a positive charge. Oh, pardon me. We're going to have a negative charge. I don't know. Why would it do that? Okay, sorry. So we'll have a negative charge on this oxygen, and we'll have a positive charge on the carbon here that was participating in the double bond. And so there is one more resonance structure to draw here. And so that is going to look like this. Sorry, let me redraw this. Okay, so the other resonance structure that we could draw would look like this with the double bond there. And so now we've placed the positive charge right there, and this oxygen is still going to have a negative charge on it. And so in this third resonance structure, the final one that I just drew there, the positive charge, it is on the carbon that we're looking at, right? So this proton, the proton that's, well, let me actually just draw the proton. So it's this proton that we're talking about in this problem. And so, as you can see in this third resonance structure, this proton, well, the carbon that this proton is attached to is now the seat of a positive charge. And so, in this resonance structure, this proton is deshielded. And since it's deshielded, oh man, this lag is killing me. Well, anyway, since that proton is deshielded, a consequence of that deshielding, there we go, is that it's going to show up further downfield than we might expect. So that proton is deshielded because it's attached to a carbon that has a positive charge on it in this resonance structure. And so remember, of course, this molecule is going to exist as a hybrid of these resonance structures. And so there is always some deshielding going on there. And so that's why the signal for that proton shows up further downfield than we might otherwise suspect. And that's the answer to part B here. And again, part A is to the left here. The splitting pattern would be a doublet of triplets. And that's the answer to chapter 14, problem number 79.